Hello, my name's Emil. In my previous role, I was an SRE. I'm now a developer working on OpenCensus. I'm still on call for stuff. So I'd like to talk to you today about OpenCensus, which is a set of libraries for instrumenting applications. And in particular, I'm interested in applications that are built out of microservices. So if you have a front end that's like a web server and it talks to a back end like a database, then that's two microservices. That's roughly how I define it. And microservices are pretty great. You can have 3 different teams all working on their own parts, and each part works in sync with the other parts to make a whole system. Each team can tune and tweak their application separately, and they can share common resources like running across the same set of computers. They can use common infrastructure like Kubernetes or a common storage layer. And that's roughly what microservices are and why you might want to run your system as a set of microservices. Not everyone does, but we do at work, and that's what kind of motivated a lot of this. So inevitably, we're going to add more components, either because we're adding features or because we need to scale up, and so we have to add things like caches and load balancers. So now we're in a situation where we have 10 different teams all working on their own parts, and each part still works with the other parts, but no one necessarily knows what those other parts are doing. It can be hard to keep sort of the whole system in your head. And so how do we manage this? So in this example, a request comes in from a user into the top of the stack, and it needs to flow through multiple layers of software in order to generate a response. So the work fans out to multiple services. It then fans in to common backends. Some of the work can be done in parallel. Other work has to be done sequentially because one request depends on the previous reply. It becomes difficult to reason about. It becomes hard to understand what's going on and to find hotspots and bottlenecks. So to debug a request in a distributed system like this, we want to trace the request from the moment that it enters the system and see all of the places where it goes and how long it spends in each place. So this is essentially what distributed tracing is. Here's an example of what a distributed trace looks like in Stackdriver. So this shows us the topology of the application. You can see at a glance which operations are blocking the next step while other ones are happening in parallel. You can get a sense of which parts are slow and whether that's affecting the overall latency. Right? This shows us where to optimize because not everything is on the critical path. So if you're running a distributed system in production, this is really helpful. The whole tree is called a trace, and the individual operations are called spans. Like in this example, spans often correspond to RPCs being sent between different microservices, but we can also create a span just to track a unit of work. So distributed tracing starts by assigning a trace ID to every request that enters the system, and we try to do this as early as possible. For every sub-operation that we perform while we're servicing this request, we create a span ID. And then we need to propagate the trace ID every time one microservice calls into another. We also have to propagate the span ID in order to track the parent-child relationships between the spans. So these two IDs together, we call this the trace context. And we can put it in an HTTP header if we're making a remote call, or like gRPC metadata, something like that. Every service then exports its spans to some sort of backend, which will assemble them into traces. In the previous slide, we used Stackdriver. The propagation has to be done consistently, because if we miss any of these steps, then traces are broken, and the usefulness of our distributed tracing is greatly diminished. So tracing is about following a single request as it flows through the system. The other part of the story is metrics. So when most people start out with monitoring, they start out with black box monitoring. So for example, on Google Kubernetes engine, you'll get some default metrics automatically. And here's an example of what that looks like in a Stackdriver monitoring. So these stats might tell you something useful, and they might correlate to what your system is doing, but they're unfortunately pretty limited. So everyone's familiar with these system-level metrics like CPU usage, disk I/O, RAM, stuff like that. But these probably aren't the metrics that you or your users care about. What we really want to focus on is application-level metrics. And probably the two most important ones are errors and latency. We would like to be able to get these automatically from our RPC or HTTP framework. We might additionally have custom metrics that are application-specific, like the length of a queue. So when we talk about application-level metrics, this is the sort of stuff that can't be extracted directly from a VM or a container. It requires instrumentation. So this talk is about observability, and the two pieces of observability that I've presented are tracing and metrics. Tracing is about tracking a single request at a time through the system, and metrics is about tracking performance across the system, like what's my 90th percentile latency, how is it changing over time? The good news is there are tons of vendors and systems out there that can help you solve these problems. What makes observability difficult is getting traces is hard, and solving this problem across many implementation languages is expensive, even for vendors. Without consistent propagation between systems, we can't share instrumentation that's developed elsewhere or interoperate between traced services. We want to make it easier to extract stats from apps, and especially from common frameworks, so that they only have to be instrumented once. And if you want to change backends, you get to do all of this all over again. So let's talk about OpenCensus. OpenCensus is open source. We have one set of libraries. There's one library per language. We currently support these 7 languages. There are more planned. Each library tries to be idiomatic for its language, but while using a consistent set of names and concepts. And we have clear APIs for tracing and for metrics. We have automatic integration with popular web and RPC frameworks. OpenCensus takes care of propagating the trace context, and it automatically measures things like latency and errors. We've got exporters for different backends. So for example, you could send traces to Zipkin and stats to Prometheus. And we have this thing we call Z pages, which can be used to look at real-time traces and application health. And I'll show you a demo of that later. So now that I've described tracing and metrics, I can introduce another useful concept that builds on top of this, which we call tagging. So a tag is a key and a value. One or more tags can be set by any component in the system, and they're automatically propagated to child RPCs. So in this example, you'd assume that at the blob storage layer, you could produce a time series of the latency of like read blob RPCs versus write blob RPCs, right? Because they're different RPCs. That should be one of the dimensions. With tagging, we could further break this down, right? So we could get read blob latency caused by authentication versus caused by reporting. And really, you can introduce any kind of custom dimensionality that you need to instrument in your system, right? That's specific to your system. And most importantly, this can be done with just one code change. We just have to insert this tag in the auth microservice, and there are no changes required to the backends, right? It will propagate through the RPC system. In the Go library, OpenCensus provides support for pprof. So this is an example of CPU usage in a Go RPC server, broken down by 2 tags. One of them is the RPC method, and the other one, we call it originator, but it's essentially like, you know, which system the request originated in. So I'd like to give a demo. This is a fork of the gRPC example that comes with the OpenCensus libraries. So I'm going to run an RPC server in Java and a client in Go. And for stats, I'm going to run Prometheus on my laptop, and traces are going to go to Stackdriver. But it could be, you know, Zipkin or another backend. Okay. Can everyone see? Okay, all right.
Probably make it bigger.
I don't think I can manage that, sorry. I think, is that legible? Is that all right? I'll talk through it anyway. So this is the RPC server in Java. This is what the code looks like. It's essentially a handler for this hello RPC. This is an example. So we simulate doing work just by sleeping. We sleep 20 MSEK plus random of 30. What I'm going to do here is I'm going to introduce another annotation so that you can see that in the output. There you go. And fingers crossed. And then execute. Sorry, I'm not actually a Java person. Just, yeah. OK, we're in business. So the server's up and running. What I'd like to show you now is what the Z pages look like before any RPCs have been sent. This is trace Z. This shows spans. These spans are capturing sort of stuff that's happening in the background. What's missing here is the hello RPC, because we haven't sent those yet. But I just wanted to show you what this looks like while it's empty, in a way. And the other one that's interesting is stats-z. So these handlers are provided by the OpenCensus library. We have measures here, which are things like number of bytes, number of requests, latency. This is the RPC server. If we look at server latency, so this is a view, which is an aggregation of statistics that's going to get exported. At the moment, this view is empty, because, again, we haven't sent anything. So, sorry, I was hoping that, whoops. I was hoping that I'd have a little more res to play with. So on the client side, this is the client. It's written in Go. It initializes some exporters. It registers views. These are the statistics that we're going to export. It's going to serve a Prometheus metrics endpoint. And the actual RPC happens here. So this is what we call the hello RPC. So that's running. The other thing I'm going to do is fire up Prometheus. So this is a very simple config. It's just going to scrape the client, not the server. The client is the one exporting stats. We'll fire that up. OK. So if we go to metrics, so this is the client. For those of you who haven't played with Prometheus, this is what the Prometheus metrics page looks like. It's essentially a text file. It's like this key maps to this value. If I hit a 5, you should see the numbers changing. 24, 25. You can see here that there's actually 2 RPCs in play, right? Say hello is the one that we're sending. But the client is also uploading spans into Stackdriver, and we'll look at those a little later. So if we go to Prometheus, look for latency. Neat. So this is cumulative latency, so we need to take the rate. And that's the derivative of the sum of all the latency spent. We need to divide that by the count. I messed it up. There we go. And that gives us the average mean latency per RPC. Should be about 35, because it's 25 plus a mean of 15. So that's about what I expected. And you can see that it's broken down by the 2 different RPCs, right? So if we had more RPCs, they would show up. We could add tags to further break these lines down by whatever other dimensionality we want. If we look at stats-z, I'm going to reload this. So we have data now. This is the say hello. The count should be changing. And we build a histogram, which is exported to Prometheus, but I just wanted to show you the mean because it's easier. The other thing is trace-z. So this should now, when I reload it, have the RPC that we're sending. See if I can, sometimes you get lucky and there's one that's running. Missed it. Anyway, this is broken down into latency buckets. and also if there's any RPCs that have errors, those get sampled as well. This is all coming out of in-memory data structures inside the Java server. If we look at these, so this is what, these are spans, right? They have a trace ID, they have a span ID. The parent span is the client generated its own span with a span ID, right? And that sets up the parent-child relationship. And annotations are essentially like a log per span. And you can see here, we got a random of 46. This happened 46 MSEC later. I've worked on systems that are instrumented this way. And if you choose your annotations judiciously, this is super useful for debugging because you have a bunch of log lines and you have an unexplained sort of delay between two of them, and that tells you where to look. And quite often it's something like received reply from database 1, received reply from database 3, long gap, received reply from database 2. Now you know where to look next. The final bit I'd like to show you is what this looks like in Stackdriver. So I'm going to reload this and see if anything's been uploaded. Oh, yep, it's just a little, oops. I'm sorry it's a little bit cramped. Maybe I can zoom out or something. There we go. So this is a tree. You can see we have two microservices participating in this trace. There's a client and the server. You can see here the annotation, and you can see that it's all along a timeline. While this sent span is selected, this comes from our Go client. When the received span is selected, this is the Java server. So all of this stuff is available today via OpenCensus. You can instrument your distributed systems. You can do it across languages. Traces propagate. You can add annotations, and it's really handy for debugging. And we've got stats, and we've got multiple exporters, so you can you don't have to use Stackdriver. You could use Zipkin. You could write your own. It's kind of like a plug-in system. OK, cool. Sorry, I'm just coming back to my slides. OK, so to recap, I talked about what distributed tracing is. I talked about application-level metrics and why they're useful. I talked about using tagging to break down metrics by arbitrary dimensions. We talked about context propagation, which enables all of these things. I went through a demo that showed a distributed system written in 2 different languages. And I showed you Z pages, which I really like, because I use them daily in my previous role. It was really like the bread and butter of debugging. OpenCensus has a bunch of future work planned. We would like to support more languages. We would like more frameworks to be instrumented out of the box. And we want client libraries to have instrumentation. So for example, if you use like a Redis or a libMySQL client, it would be really great if that just produced spans and stats that are meaningful to that domain. There's this thing called trace context, which is we're trying to define a common context propagation format for trace IDs and other things like tags. For HTTP, this is passed in a header, which we're trying to standardize. There's a thing called Open Metrics, which is being led by the Prometheus community, and that's in its early stages, but OpenCensus would like to support it. We know that many existing systems use logs analysis, so we're working on logging modules that insert trace IDs into logs for correlation for people who haven't quite worked up to full-on distributed tracing yet. And we have APIs for tracing and metrics. We're experimenting with an API for logging. That's not quite, it's still experimental. And we don't upload all traces. We take a random sample we basically decide at the start of an operation whether to sample it. We're experimenting with some different approaches to sample more interesting traces. Like later on in the operation, if something is running slow or if there's an error, it's much more valuable to get a trace of that than a trace where nothing went wrong for debugging purposes. So that's about it for my talk.